Hello there again, Math Analyzers. Chapter 5, Lesson 5 notes. Today, all about the Argand diagram, because, when it comes to math, we either name things after the thing that they are doing or the person who started doing it first. Argand. So, because imaginary numbers, complex numbers, imaginary units, right, aren't rational, they're not irrational, they're not real numbers. They have their own coordinate plane set to look at how they behave with their real unit added to their imaginary unit, making it complex. Okay. We form kind of a vector system by doing that. And a vector is just a ray from the center, from 0, 0, the origin, out to where that point is on our Argand diagram. The Argand diagram is just like an XY axis, but the x-axis is your real number axis. That's your A in A plus BI form. And the y-axis is the imaginary axis, your BI in A plus BI form. So essentially, think of it this way if we're dealing with A plus BI form. Okay, that's the axis that we're looking at. So to plot the point, you take the real number, and that's your x coordinate. You take the number in front of the I, your B value, as your y coordinate, and that's what you graph on this particular coordinate plane, the Argand diagram. It's just an imaginary number coordinate plane. That's what the Argand diagram is. Okay, and we're going to be graphing vectors. All right, so that's what we're going to kind of be looking at today. The next lesson, lesson 6, is all about measuring that distance of that vector. Okay, that's what we're going to be doing. So these could really be in conjunction with each other, but we're going to take our time with it. Okay, so take 2 separate lessons to talk about it. Now, when you're graphing a complex number, okay, the real number, like I just said, is your A value. Oops, didn't pull that up all the way. Sorry about that. Your real number is your A value, or your X in the coordinate. Your B value is your Y in the coordinate. You still graph that particular point, but what you then do is take your straight edge from the origin out to that point and then put an arrow at the end. You create what's called a vector or array from the origin out to that point. And then when you label it A plus BI form. Okay. And that's what we're going to do. See, this is a distance from the origin. And that's why I say we'll tomorrow look at that as a distance. Okay. All right. If I were asking you to graph 2 plus 3i on an Argand diagram, that is what you would do. 2, 3 would be the point you graph. 1, 2, up, 1, 2, 3. And then you draw that vector from the origin out to the point and then put the arrow. Just like that. Now label 2 plus 3i right on the graph. Just like that. That's what we're doing. So here is an Argand diagram with 5 different complex numbers graphed, okay? And then their vectors created. So this is already done for us, but this is some examples of what to look at, right? So we're not technically graphing the I part of the BI part in the form because it's already part of this. This is in some circles called the YI axis. It's already assumed that these are imaginary along the y-axis. So any of those points, any of those pieces of the points, we already assume that there's an I attached to them. Now, what if you're just graphing the number 3 in an Argand diagram? Well, that's really 3 plus 0i, no I value, which means it's just a point on the x-axis, the real number axis. Let's say you're graphing just an imaginary unit. That's really the same as graphing 0, 4. Just the y value gets graphed, right? Because it's 0 is your real number as a part of that. So it's really 0 plus 4i. So 0, 4 is what you would graph. You do still have to draw the vector even if it's on an axis. So you still have to draw the vector from 0, 0, even if it's on an axis. Okay? Notice how every single one is labeled with its imaginary number or complex number every single time. Okay, take note of that because that's how we're going to do all of these every single time. Now, of course, I've got 3 different ones here that I'm going to do. I'll just do each one in a different color because why not? Right? Start with my signature aqua. Here, let me move that out of the way so you're not distracted by the pretty colors underneath. All right, so 3 plus 4i. Okay, that is 3 comma 4. So I go to my Argand diagram, 3 comma 4. There it is. Now take my straight edge. Covered my straight edge with all my pretty pages. Blah, blah, blah. From 0, 0 out to 3, 4, and an arrow and label 3 plus 4i. Done. Next one, -1 plus 2i. That would be the point -2 comma, -1 comma 2. So -1 up to 2 from 0, 0. I graph my vector. Probably could have made bigger vectors here, but there I go. And now I label -1 plus 2i. Got it. Last but never least, 3 minus 5i is really 3 comma -5 as a coordinate. So 1, 2, 3, down 1, 2, 3, 4, 5. From 0, 0, use that straight edge. Arrow at the end, because that's my vector. That's where it stops. And 3 minus 5i is the label. Okay? Make sure you label. Make sure you label. Make sure you label. Did I say it enough? Should I pound on a table more? That would certainly be more like some of your other teachers, right? This is where it gets fun. Because there's this whole thing with vectors, right? When you've got 2 vectors on a graph, they can form a parallelogram when you do their parallel vectors and connect. So this vector right here is -4 plus 2i. That's this distance over here. This vector over here is 3 plus 4i. So notice that's this over here. If what you then do is take this vector and its same exact thing and literally put it right here and then stop it where it ends. And then you do the same for this vector. You take it across and you put it right at the end of that other vector and stop it where it ends. This point right here is the point of the consultant vector, meaning if you added those 2 things up. Okay? That's what you're looking at with adding and subtracting. Okay? So with adding, it's taking them and putting them end to end this way. With subtracting, it's going the opposite direction with those, okay? With subtracting, it's back the opposite direction. And so that's what you'll see from these 2 pictures, okay? This is, resultant, the resultant vector. I used the wrong word. This is exactly what would happen if you add -4 plus 2i with 3 plus 4i. And you get -1 plus 6i, which is exactly where those 2 vectors met when you put them end to end. It's the diagonal in that parallelogram. It's the diagonal from 0, 0 up to that point where those 2 other sides meet. That is the vector that is your resultant vector. I said consultant, didn't I? My gosh, am I thinking about business or what? Okay. That's adding. Now notice I could just add those 2 complex numbers up and I know I get -1 plus 6i. But here is where we're talking about how does this apply to this vector concept in parallelograms. And so again, subtraction is adding the additive inverses, right? So that's actually what I graph is those additive inverses of those. And then notice that is that vector over here is the resultant of the additive inverse. This is the one you were subtracting. So technically what you needed to graph was -3 minus 4i. So that's what we used with -2 plus 2i. And we did that same piece where we took its exact distance and just put it at the end of that vector. And we took this exact distance and put it at the end of this vector. And when you do that, you get the answer to subtracting those two original vectors. Again, this was the original, but I needed its additive inverse if I'm subtracting because technically these are both sign changes. And that's what happened back here. The sign changes on both of those. Okay, again, this is just the result of me typing into my graphing calculator, -2 plus 2i minus, and I'll put this in parentheses because it has to be distributed, 3 plus 4i. Same exact thing. Let's do it. Let's do it. Okay. Here's my arcane diagram. Here, I'm just adding, okay? So I just want to be, I'm just thinking, maybe I want another arcane diagram. Hold on. I'm going to want another arcane diagram. Let me grab that. Move. Now when I do this, I'm going to have to move it down further. Yeah, of course. All right, I'm going to try to line this up so that you can see my lines underneath a little bit because the copies, of course, did not copy the grid part of the coordinate grid, which I'm like, that's pretty nice. Look at that. Anyway. All right, so what I'm going to do is I am going to graph my first one, graph my second one, and then I'm going to move them to create my resultant. And we're going to check by adding in our graphing calculator that that is the correct resultant vector. That's what I meant to say, vector. How about we get better screenage up here so that you're not seeing my background over there, right? Okay. Let's graph this guy first. So this is 3, 4. 1, 2, 3. 1, 2, 3, 4. And we graph this guy from 0, 0. Okay. Now let's graph this guy. So this would be -7, 5. So 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5. Now, from 0, 0 out to vector. Cool. So those are my two originals. My black is going to end up being my resultant. Let me just label first. 3 plus 4i and -7 plus 5i. And what I'm going to do here is I'm just going to take this and now starting from here, I'm going to mesh these two guys up, right? So let's see. I started at 0, 0 here. I'm going to start here, and it was up 5 and left 7. So up 1, 2, 3, 4, 5, left 1, 2, 3, 4, 5, 6, 7. So this is the same vector, just put at the end here, right? See that? Parallel. Now I'm going to do the same thing with this guy. So I'm going to move him starting right here, and he was up 4, right 3. So up 1, 2, 3, 4. That makes sense, right? 1, 2, 3 makes sense, right? So he ends up here. And the resultant vector is from 0, 0 to right here. I'm just going to do one of these this way, and then the rest of them we're just going to add, just so you know. There we go. So from there, this guy is -4, 9i. So this guy is -4 plus 9i. And just to check to make sure that's correct, I'm just going to type into my graphing calculator exactly what I had here. 3 plus 4i plus -7 plus 5i. And there we go. Exactly what I got. That's how those values, that's how that particular vector value gets found. It's the diagonal in the parallelogram that gets formed by these two vectors. It's the resultant vector of those two. Okay. Now, that's the only one I'm going to do that way. The rest of them, I'm just going to find their answer and put it on the graph. Now, I do have another copy of the graph for me to do it this way. That's my original. But I'm going to do this copy on it right here just in case I need my original for anyone. Okay. So this time, what I'm just going to do to graph this guy is I'm just going to actually add my like terms. So -5 minus plus -1 is -6. And 8i minus 4i is positive 4i, which means I'm going to graph the point -6, 4. 1, 2, 3, 4, 5, 6, up. 1, 2, 3, 4. This is the resultant vector of those two. And label. And again, I could find that answer in my graphing calculator. I just chose not to. And same here, right? This is really a -3, and this is really a positive 12i. So now when we combine like terms, 6 minus 3 is 3, and -3i plus 12i is positive 9i. So the point I'm going to graph is 3, 9. 1, 2, 3, all the way up to 9. Vector starts at 0, 0, and arrow at the end. 3 plus 9i. That's all we're looking at, is graphing those particular pieces. So when you go to do this tonight for homework on the sheet, on the homework sheet, which I had one, but I guess I put it away already. When you go to do this tonight for homework, all I want you to do is find the two added vectors, unless you're given one single a plus bi form to graph. If you're asked to add them or subtract them, all I want you to do is actually add them and subtract them and put their resulting point, just the resultant vector, on the graph. If you want to do what I did with the adding the two, like I did in this example, you are welcome to, but you do not have to. Just the black version, which is having added those up, is all I'm actually looking for you to do. Okay, but I was showing you where that came from. I needed to show you where that came from. Why is that what we get when we add? And then in the next lesson, why is that important is the last piece. Okie dokie. Argand diagram named after Mr. Old Argand. Look him up. I swear he's a real person, or was. Not anymore. All right, guys. Good luck. Let me know what you need. Think you'll be okay, but let me know what you need and if you need it. Bye, guys.